everyone, today to our second part of hybrid and plug-in electric vehicles. We're looking at today more in the transition of power from the engine to the wheels. So I'm not going to get into batteries too much. I think that's it's a subject on its own. But what I want to do is get into the power transfer units, into the gear reduction units, and final drives and so on of the hybrid vehicles that you will be essentially teaching about or talking about to students in your classroom. So I want to get right in.
Oh, Dave, you're muted out somehow.
Okay, am I back?
Yep.
Okay, sounds great. Okay, I'm just going to close this window down here. So today's objective is identifying the main types of hybrid powertrain. So we're going to focus mostly on Toyota and Honda because many manufacturers basically deviate from these types of technologies, whether it's fundamentally or directly. We're going to talk a little bit about series parallel as well as power split hybrid vehicles. And, one thing I always say is not all hybrids are built the same. We have various different types of hybrids, as we just mentioned, series hybrids, parallel hybrids, as well as power split hybrids, or otherwise known as series parallel. So getting right into it here, we're going to look at, oops, did I pause myself again? Hang on a second. There we go. So why hybrid power flow matters, and it's because of how the electric drive units and so on deliver that power, whether it's through gear reduction, a CVT transmission, or electrically controlled drive output. They all vary in some manner. So that's what we're going to be doing today, is we're going to be looking at a couple of the different types of these systems. So hybrids now dominate, and that's the big thing, is a lot of transitional, consumers looking at getting into something more economical might not want to jump directly into an electric vehicle. So they opt to go with a hybrid option. Hybrid options offer many benefits, as well as, some of the, the downsides of a hybrid. It still requires your oil changes and so on. But the thing is with a hybrid, it does give peace of mind to range anxiety, performance, as we can see some of the new cars coming out that are hypercars and performance vehicles use our hybrid powertrain, supplementing both technologies into a very efficient but also very powerful platform. So we're going to see more and more manufacturers moving to hybrids. As we continue to see in Ford and some of their trucks, they've gone more hybrid or extended range electric vehicles, where they have their gasoline engine essentially powering the electric motor and directly driving the wheels. One thing the students do struggle is visualizing power flow. Like, how does this power flow come from an engine and electric motor, but they're not coupled together. And we're going to look at that and how that's used, and also understanding some of the planetary gear sets that some of these series parallel hybrids use. The idea is to simplify torque delivery paths. And this is a quick little, I was going to build one today, but just didn't get a chance. Just get two cones, you put them together, put a drill on one end, secure each end of them. And then what you do is you put a rubber band on it. And what's really neat about it is you set your drill to one speed, low speed. And then as you move the drill, the rubber band over these cones, the output of the wheel speed changes. And it's a very simple way of showing how basically a CVT works. And the advantage I always talk to students about is how I can keep one speed on the electric motor. And as we know, as the electric motor being the drill, we have that maximum torque, we have like all that power available, and I can output drive speed based on my position of this rubber band. And essentially that's the simplicity of, a type of CVT that's out there. What is a true hybrid? And this is a big question that does come up a lot. It's basically using two differing technologies, being that of the electric motor and the gasoline engine, to supplement each other, but they can work independently. So on our gasoline engine can drive the wheels, or they can be driven by the electric motor, or a combination of both. And this is what a true hybrid is. It gives the ability to do all these different things within the single platform. Many manufacturers will manipulate what a true hybrid is, and we're going to look at a couple of them in a few moments here. One thing we do have is I know my videos come in very choppy, so I'm not going to go play the videos here, but I was going to be using some demonstration using our hybrid trainer. So, which is basically a planetary gear set with a split, which some of you may already have, which is great for students to interact with the trainer to show power output to the wheels through different modes of operation. So, oops. Yes, I think it's too choppy for you guys. Jimmy, is that choppy on your end?
Yeah, I mean, it's a little choppy.
Okay, that's fine. These are now one of the things that we have on our website. If you go to Consulab's website and you go to the end of the page, we have a YouTube channel. And the YouTube channel has all these instructional videos on there as well too. So maybe I'll put the link up at the end of this presentation, and then you can use it as a resource if you're in the classroom, or if you have some of this equipment, or you just want to be able to talk with some of the technology that's out there. Oops, I was going to try and get this. It's going to let me move ahead. So one of the things about the power split device is basically a simple planetary gear set. There's nothing special about it. Toyota uses it. Many manufacturers also use this type of setup. But like I'm going to say, remember the saying, engine's in the carrier, generator in the sun, and of course, wheels on the ring. So when we were talking to the students about what actually drives the wheels is actually the ring gear on the electric motor if it's set up as a power split device. That means anytime the wheels are turning, you're turning that ring gear. Now, whatever that ring gear is attached to is also turning. And that's very important, especially in the safety, moving vehicles, and so on, is how these systems interconnect with each other. And of course, we talk about the generator in the sun gear being the center gear of the planetary gear set. And essentially, that's going to be tied to another, a power output device. So we're going to talk about that, and see how this all comes together in an operational fashion. So in a typical power planetary gear set using a series parallel hybrid, basically the engine is started by the electric motor. In the case of this one, it has two electric motors. You have your MG1, MG2. MG1 and MG2 are very different. In this case, a Toyota Prius or RAV4 or whatever, a Toyota platform. The MG1 is used for two functions, one for charging the battery and two for starting the gasoline engine. Now, the engine itself doesn't have a conventional starter in it. That means that the MG1 is the starter for the engine. And the thing is, because the motor is so powerful and so fast to respond with its torque, it can spin this gasoline engine up to about 1,200 RPMs in less than a second. So very, very fast operation of the engine. Starting speeds are incredibly fast. If you're going to do a compression check or something on a gas engine in a Prius, for example, you have to use the scan tool to go into a compression check mode, which will reduce the speed of the engine to be able to do that type of testing. So, but anyways, going through high voltage battery, MG1 goes through a power split device, which then in turn turns a gasoline engine. So MG1, being the sun gear, is directly tied to essentially to the gas engine. So when we're talking about, MG1 is tied directly to the sun gear on this planetary gear set. The engine is tied to our basically inside our planet gear. So at the same time as we're turning the gas engine, we're turning basically the planet gears, and then we're also turning the MG1. So they're kind of tied together, and that's really important for vehicle operation as we move forward. Low speed electric, once again, allows a high voltage battery to go through the inverter to power the electric motor, MG2, which then drives our wheels. Very simple operation. Normal hybrid drive uses a combination. So MG2, which is tied to the ring gear, engine is tied to basically our carriers. And then, of course, our MG1 is tied directly to the sun gear. So, and in this operation, even though the MG1 isn't used to do anything with the engine at this time because the engine's outputting power, MG1 is also supplying power back to MG2 or charging the battery. So it can do a kind of a combination, but typically MG1 is helping supply energy to the MG2 for hybrid normal drives using the gas engine and the electric motor to do both functions. Full throttle acceleration, high speed, basically involves more or less the MG2 becoming more powerful, more current flow, turn the engine faster, as well as we also have the engine outputs power. So we're getting maximum power from the engine, maximum power from the electric motor, and MG1 is also turning to once again help supply maximum voltage output and current output to the inverter to help MG2 maximize its performance. Now, because we have an engine that's sitting there and spinning, we don't want the engine to over rev itself. So what we use is we use MG1 to help control the speed of the engine. And this is something that's the really good show how these systems work together in the engine itself, how they supplement. So MG1 can actually start to spin the sun gear backwards, which will slow the carrier down, which then ultimately slows the engine down, which allows the engine to reduce its speed, as well as creating efficiency and also helping create that gear ratio for higher speeds as well. Regenerative braking comes from our MG2. Basically, once releasing the brake pedal, you have regen, which will slow the vehicle down. But that energy also, rather than transferring it into heat, will now become energy that goes back to the battery and is stored in the battery for, for future use on the next drive or whatnot. If the battery is to a point where it's almost fully charged and the regen can be reduced, in driving, so people will also notice they may need to use their brakes a little more if the battery is a little lower than what can be accepted by the regen energy coming from the MG2. Reverse is basically reversing the electric drive motor. So going counterclockwise to the ring gear basically will allow the vehicle to go in reverse. But in a lot of cases, in reverse, you'll hear the gas engine start up, especially in some of the earlier Toyotas. The gas engine will then supply power through the MG1, which then supply power to the MG2. So there is no direct connection between the engine and the final drive in reverse. The only purpose would be is to spin the MG1 to help supply power, where reverse is full electric. So that's just a little bit of a quick overview of the power split device applying to your gear. So I'm going to get into a little bit differently here, but just want to run through that a little bit with you to show how the power is distributed on the power split device system. One thing I do like to do is if you're in the class teaching about different types of hybrids, whether it's series or parallel or combined hybrids or a series parallel hybrids, is to get the students either draw it, you draw it on the screen, or use a PowerPoint like I'm going to use here, just to show what each one is, because sometimes a visual of showing a student that we have a combustion engine, goes to a battery, and battery to an electric motor, and then the electric motor to a gearbox, and the gearbox to the wheels. And that's a simple series hybrid, hence series being one path. Now, if I look here, a parallel hybrid, a little different. I have my combustion engine, I have my gearbox, I have my drive unit to the wheels, so just like a conventional vehicle, nothing different. And then I slap in the battery in the vehicle, I put an electric motor, in place, and that electric motor can also drive the vehicle as well too. So I have a combination, parallel two paths to the final drive. So, and then of course in this case here, also the combustion engine can also act as a generator too to help charge the vehicle. Typically powered parallel hybrids, they can drive either with electric and or gas at the same time, but the problem is it can't charge its battery while driving. So because it has its options, either it's going to run electric, it's going to run gas, it's going to run gas and electric, but it can't charge its battery while running. So it either have to, basically turn off the electric motor and use the combustion engine as a generator if it's equipped to do so to charge back the battery. So it depends on the type of parallel hybrid that's out there. Series parallel hybrid, once again, usually has a combination of two electric motors. So in this case here, we have our combustion engine, we have our battery and our gearbox, we have our electric motor, and then we have another electric motor. So in this case here, one motor may be used for charging and starting, and the other electric motor is used for driving. So in this case here, I have a power split device to help take all this different power flows and put them into the gearbox. So in this case here, a combustion engine to the power split device to the gearbox. Very conventional, simple, almost power split device being a planetary gear set to the gearbox and drive the wheels. But now also that combustion engine can also turn an electric motor, which in turn can charge the battery, which in turn can supply that energy to the electric motor, which then can put it to the power split device, sharing the power output loads to the gearbox, as well as the electric motor that drives the vehicle can also be used as regen, as well as in the other two different types of systems. So once again, series parallel hybrid, a best of all worlds all at once. Now, at the end result, we have power output to the wheels. So, and most gearbox are just basically gear reduction units. They can be, and they usually have the final drives in them as well too, which are usually open carrier units. So hybrid series, parallel, full hybrid, complex system. Lots of different components are working together, but it's more about strategies than it is more about parts. So there's a lot of strategies that go inside basically a series parallel hybrid vehicle. Toyota has a power split device, essentially, within that system, which we've been talking about. And this is a good example of one, if you ever had to demonstrate in the classroom, this is a good example of a power split device. Obviously, this is very similar to the Toyota, but allows you full operation of showing the output of the power flow from an electric motor to the gasoline engine and how MG1 can supplement both of them, one controlling speed and two also an engine starting. Toyota low-speed operation, once again, very similar to what we talk about electric drive. One thing about this system that we're looking at here, the ring gear on the outside is directly tied to the final drive of the vehicle's wheels. So anytime the wheels are turning, MG2 is turning. So it's really important to understand that if you're pushing a hybrid or electric vehicle and you're moving it at a good pace, if you're trying to tow it, and those wheels are on the ground and those wheels are turning, you're also turning the generator, and it can cause significant damage to the inverter or even to the electric motor if you're towing it above a speed with the vehicle off, especially when it's off. So it's important to make sure that you follow manufacturer procedures when even pushing the vehicle across a parking lot or inside the shop to make sure that you're not generating that energy back into the system. So this is a good example of this low speed driving. Battery powers the MG2, which is tied directly to the ring gear. As we said earlier, is that the ring gear is tied to the wheels. And of course, the engine is off, the gasoline engine is off, and then you have basically electric drive mode. So very simple setup for how they get into electric driving with the hybrid vehicle. Now, there's another system out there that's an earlier system. I'm going to talk about the eHEV as well in Hondas, but this early IMA system was unique in that parallel sense that I mentioned earlier. Basically, Honda used a lot of engine technology. We talked in the first part, talking about the Atkinson cycle engine, the efficiency of it and how it worked. And, essentially the electric motor basically assisted that gasoline engine to give the range and boost and so on. And yes, it could run full electric, this early system, even though the motor's in between the engine transmission. And it used engine technology to be able to run full electric at very low speeds and very short range. Because these batteries back then were very, very tiny. Nickel metal hydride batteries really didn't have a lot of capacity, but it was more or less for assisting the gasoline engine. So, but one thing is, the problem was you cannot charge the battery and drive the wheels on electric with the system. So that was a bit of a downside to this parallel hybrid system. So these early systems were basically single motor squash between the engine and transmission. We can see the belt in this CVT transmission here. Once again, mid 90 or I'd say early 2000s and up, even though these were introduced in early or late 90s. But once again, very early type of technology. Work great for boosting. You'll see even some hypercars and that will use a very similar design just to get the boost from an engine, and then the engine takes over. So once again, there's some advantages there. One thing I like to point out is when you see 3 cables coming out of a transfer case, that means the inverter, the controller, lives outside of that transfer case. So if you see 2 cables going into a drive unit, the inverter lives inside that drive unit. So since manufacturers are different in how they do it, but I see the 3-phase wires here. So that means this inverter would be external to the drive unit. So that means it'd just be the stator, the rotor, and essentially the cabling going into it. So both types of these early hybrids use different ways to use hybrid power. Honda uses engine efficiency and strategies. Electric motor relies on the engine. Toyota a little differently, engine efficiency and strategies. Once again, Atkinson cycle engines, but relies more on the electric motor. So once again, it's different types of worlds back then. Today, they've come a long way in these hybrids, and we're going to take a look at that. Some of these new hybrids are plug-in now, so they can be plugged in. They drive a lot further. They have bigger batteries. They're using lithium-ion batteries. Same driveline technology really hasn't changed a lot. Obviously, it's changed in the sense of fundamentals, and what they're actually doing with the motors and the gear sets, but essentially still a battery, still a gasoline engine, still a final drive unit. So a plug-in hybrid electric vehicle essentially is an electric vehicle on its own, can drive some of these cars can go pretty good range, in some cases 60 kilometers, some of them are even 60 miles. So depending on the manufacturer and how big the battery is, it really comes down to how big that battery is in this vehicle. But Toyota high-speed operation and Honda high-speed operation had differed in newer technology vehicles. So once again, Toyota high-speed operation uses a combination of its electric motor and gasoline engine to manage its speed. So once again, the MG1 manages engine speed, engine drives a planetary gear set, and of course, MG2 assists and applies torque in the Toyota system. Simplistically, Honda's high-speed engine has changed. They've gone to what we call an eHEV. They use an eCVT transmission. Honda has now 2 electric motors in their drive units, but one of them is not designed as an electric motor. It's actually a generator. And then the other one is our regular electric drive traction motor. So Honda uses engine drives the generator. So the gasoline engine's job is to drive the generator. Generator provides power to the motor, and motor drives the wheels. So the electric motor is really what's driving the wheels in this Honda, unless it goes into full gas mode, which then it uses a clutch, which is very unique in this setup. So Honda system uses an electric motor dominant system, very different from the IMA system I just showed earlier. Engine mainly generates electricity. Its job is to turn that generator. It can drive the wheels through a clutch, but there is no direct connection in that sense to from the electric motor to the final drive through the gas engine. It has to go on its own circuit. I'll show that in a second. So how does it do it? It has a coupling clutch. So for the gasoline engine to drive the wheels, it has its own coupling clutch, different area of system. I have a little diagram here for that. And it will allow basically the engine to drive the final drive unit directly through a clutching device, or what we call a coupling device. So Honda's electric mode, very simple, just like everybody else. We have our electric drive unit, we have our battery drive unit, and then we can go into what we call Honda's parallel mode. So we can go from electric to parallel mode here. So we can see the gas engine going through that generator, and then that generator supplies power to the electric drive unit and then to the wheels. And then, of course, the traction battery can supply power as well to help power the wheels. So this system is, once again, unique. So in hybrid parallel mode, as Honda would call it, it's really more of a series type of system. Since I'm turning a generator and powering an electric motor, it's more of a series. But in this case here, I am not directly driving the wheels mechanically in this mode. I am only powering the electric motor generator to help me supply power to the MG over here, or the traction motor, to drive the wheels. So there is no direct connection from the gasoline engine to the wheels in this parallel mode. Now, if I want to go run direct gas, which is usually at a higher speed, typical on the highway, then I have a coupling device. This coupling device will then allow the gasoline engine to directly power the final drive units with this special clutch. Not really a special clutch, but it's a clutch that's within the transaxle of this vehicle. So I drew a little diagram here. It might be interesting to see how I'll try and go through it a little bit real quick here, but just want to make a point here. As we can see, the engine has a geared flywheel, which acts as a dampener, as well as it also has a gear that is directly tied to a generator. So these guys, whenever the engine is turning, this gear is turning, which is turning the generator, which is charging the battery or is helping supply power to the electric motor. This electric motor is not tied directly to the generator in any way. So when the electric motor is turning and turning the final drive, this gear can be stationary, the gas engine can be off, and that's how we get electric drive mode on this Honda. But then when we want to go into gas mode, we now have this clutch here. So this clutch here, what happens is, even though I'm still attached directly to the generator is basically a shaft hooked directly to a gear set that's tied directly to the crankshaft of this four-cylinder engine. There's a clutch in here. So when I start up the gas engine, this is spinning. Yes, it might not need to develop any power, so the inverter might not accept any energy from the generator, and that's okay. I'll show you in a second how that can work. But we do have a clutch, and inside this transmission are two oil pumps. One of those oil pumps is actually designed to apply pressure onto the plates inside this clutch unit And this overdrive gear, which is usually free spinning, it doesn't attach itself directly to the clutch here. What happens when the clutch is applied, this override gear locks up. So by applying the clutch, the fluid pressure to the clutch, this override gear locks up, which then drives the final unit. So that's how this clutch works. So it's done by fluid pressure. If there's no fluid pressure, this thing will never be able to drive in full gasoline direct drive mode. So, but just going back one in electric drive, because the gas engine spins over the shaft, right now the gas engine's off, it's locked, this is locked, the generator is not turning, and we can run in direct electric mode to the final drive. And then to get our parallel EVC mode, essentially, we can run the gas engine, turning the gear, turns the generator, supplies power to the electric motor. Electric motor drives basically your carrier, not your carrier, but your transfer gear, I guess you can call it, and then to your final drive unit. So very unique how the system works. So gasoline engine is turning the gear for the generator. Generator can supply power to the electric motor or charge the battery. Electric motor is driving the final drive. Honda's system is really a series hybrid, as much as they like to say it differently. It's really a series hybrid in the sense. So even though the only way they can drive gas is by using this overdrive gear clutch, using fluid pressure to apply pressure on the clutch to drive the final drive with the gas engine. And then, of course, on this one here, it's really a series hybrid. Gasoline engine is just turning a generator is supplying power to the electric motor drives the wheels. Very simple. So Toyota versus Honda, I didn't want to put the versus there, but this is the way it comes out. Toyota is a power split blending. Toyota still uses power split blending with their planetary gear set or their power split device. And Honda's electric motor is dominant series hybrid. So really, it falls into the series hybrid category, but it does have the availability to run gas direct to those wheels. So concluding here, just looking at a couple of things for my time, teaching hybrid system, use diagrams, use the power flow diagram, show different methods of, how the combustion engine is still relevant in the vehicle as what they might know of, and then draw out how the electric supplements it or can run on its own, or use a combination of both systems. And training aids always helps. A planetary gear set trainer is great for explaining how these power systems work. You can simulate them, even write on them, like motor. You can write engine, and you can write like electric motor. Do different things to help demonstrate that. This trainer down here is directly designed for teaching hybrid power flow through a planetary gear set power split device. Tracing power flow is also critical. If you have diagrams and so on, tracing power flow right on the screen, planetary gear set trainer as we're talking about, and using regen, using a BLDC or three-phase permanent magnet motor. I do have one here. If you're trying to explain to your systems or students, what is regen? How does regen work? And I just have a blower fan. It's a three-phase blower fan. Not sure how much you guys can see that, but it's three wires here. This is just a shield wire. There's three wires here. If you find a three-wire motor, this is off a blower fan, off a rad fan in a vehicle. You can see it spins nice and freely, but also it's generating electricity. If you want to show your students how this can work, I can spin this very easily. Just take one of the phases here and touch it against one of the other phases. I just put a switch on it. Makes it easier than me trying to, touch the wires while I'm doing this. To show the students is, here's a vehicle free spinning down the road. Yes, it's generating AC voltage. But when I go down and I turn the switch on, which essentially shorts two of the contacts, I can actually show them basically it's stopping. So I'm going to do it again. I'm going to spin it and I'll hit it. And right now, as I start to turn it, the faster I turn it, the harder it gets to turn until I release it. And then it's really easy. So it's a good example you can take from an old fan motor from a vehicle that you might have, and then just take it and snap it, and you can create that regen effect. How does the vehicle slow itself down using the electric motor? Essentially, a very simple concept in how a three-phase electric motor works. Key takeaways: hybrids combine multiple power paths, understanding energy, mechanical and electric. Flow is key, and engineers are not reinventing the wheel. At the end of the day, they're taking strategies from already existing components and making these vehicles work the way they do. And that's the end of my presentation. Anybody have any questions or comments or?
I have a question. Does using one motor only as a generator help limit the amount of batteries Honda needs to put in the car? Or what do you think the big advantage of that configuration is?
That was a great question. I think it does alleviate putting big batteries in the car by having that single generator. Definitely alleviates the size of the battery pack in the vehicle, which obviously reduces weight, which increases efficiency of the vehicle. So I think, and that electric motor is no little wimp either. That generator is, I think, I'm going to guess it's about 100 kilowatts. So it's got a lot of juice in there, and it definitely can power that 100, and I think it's 187 horsepower electric motor. So it's got a lot of energy in that little generator. So, well, thank you everyone, and hopefully you have a great rest of the week, and we'll talk to you after.
Thank you, everybody.